Hello, Chem 111 students. This is our last lecture for Chapter 4, and we are going to be looking at the last section in Chapter 4 on quantitative chemical analysis. And quantitative chemical analysis is just a method that we use stoichiometry for to find quantities of chemical reactants or products. So these are essentially applications of stoichiometry. And we are going to look at two different kinds of chemical analysis, something called titration and something called gravimetric analysis. But they're both stoichiometry problems, just applied to specific systems. So titration and gravimetric analysis are our two points that we're going to apply stoichiometry to. So first of all, titration is something that you may have done already in high school chemistry, but titration involves two solutions, and we have one solution that we know the concentration of, and one that we're usually trying to find the concentration of. So we call the solution of the known concentration the titrant, and the solution that we're trying to figure out the concentration of the analyte. And we measure volumes of titrants and analytes very carefully to something called the equivalence point of the titration, which is when all of the reactants have been used up. So we start out with a solution of known concentration, and we gradually add it to a solution of unknown concentration. As I said, you may be familiar with having done this in high school chemistry if you did something called an acid-base titration. So the equivalence point is the point where the reaction is complete, and we usually have to have some way of measuring that. So often there's something called an indicator, which is some chemical that's going to change color at or near the equivalence point. Or sometimes we could measure it with an electronic probe, for example. We could measure pH. There are other ways of figuring out what the equivalence point is. But the most common one in introductory chemistry is to use a chemical indicator. So the typical acid or typical titration that's done in introductory chemistry is an acid-base titration, where we start out with a base in a device called a burette, and this is just used to measure volume very accurately. So we have a solution in the burette that we know the concentration of, and then we have a carefully measured amount of the unknown solution in a flask that we don't know the concentration of. And we carefully add the solution from the burette to the solution in the flask until we get to what's called the equivalence point. So we slowly add base to our unknown acid, and for example, one indicator is phenolphthalein, which will be colorless in an acid, but when we add enough of the base to make the solution basic, it changes color from being colorless to being pink. And when that changes color, we know that we have stoichiometrically equivalent amounts of those two materials. So here's one of the types of calculations that we can do using titration. This one says the endpoint of a titration of 50 milliliter sample of aqueous HCl was reached by addition of 35.23 milliliters of 0.250 molar sodium hydroxide. The reaction is this. What's the molarity of the HCl? So we know this about the sodium hydroxide. We know that we have 32 or 35.23 milliliters of it, and we know its molarity. So the sodium hydroxide is our known solution here. The 50 milliliter sample of hydrochloric acid is our unknown. So I know that I have 35.23 milliliters, 35.23 milliliters of NaOH, and I know the molarity is 0.250 molar. I have 50.00 milliliters of HCl, and the question is, what's the molarity of the HCl? Now, recall that molarity is a fraction. That capital M means moles NaOH per liter of solution. So that's going to be one of my conversion factors. When you're given the molarity, you're going to use that as a fraction. So it's going to be either moles over liters or liters over moles. So in order to calculate this molarity, we start with our known solution. And this is a stoichiometry problem. So the first step in every stoichiometry problem is to convert the amounts that you're given into moles. And if I start with the 35.23 milliliters of solution, I can then multiply by the molarity to get moles of NaOH. Once I know the moles of NaOH, so I start with liters or milliliters of my solution, I figure out the moles of NaOH. I'm then going to convert to moles of the other substance, which in this case is HCl. So we can convert the volume to liters and then multiply by the molarity. Or I could have just combined these two fractions into 0.250 moles NaOH per 1,000 milliliters of NaOH. And that's the same as saying 0.250 moles of NaOH per liter. And then because the reaction was HCl plus NaOH goes to NaCl and H2O, and these are in a 1-to-1 mole ratio. We multiply by that mole ratio to get moles of HCl. Now the question asked for the molarity of the HCl. So if we look back at our original problem, we had 50 milliliters of the HCl solution. So in order to get the molarity of the HCl, we're going to take this many moles of HCl and divide it by 50 milliliters, but we need that in liters. So molarity is moles per liter. So we have 8.81 times 10 to the negative third moles of HCl. We're going to divide that by 0.05000 liters to get our molarity of 0.176 molar. So a titration is, at its core, a stoichiometry problem. Here's another example of a titration problem that requires us to find the volume of a solution instead of the molarity. So this one says, what volume of 1.420 molar NaOH is required to titrate 25 milliliters of 4.50 molar H2SO4? And I need a balanced chemical equation to do a stoichiometry problem. So my equation is H2SO4 reacting with NaOH to make two waters and sodium sulfate. This is an acid-base reaction. Now in this case, if we write down what we know, our known solution now is the H2SO4. So I've got 25 milliliters of H2SO4. And I know that it is 4.50 moles per liter. I'm going to write that as moles per liter instead of molarity, because remember that this is a conversion factor. Okay. For the unknown, sodium hydroxide, I don't know how many milliliters I need to get to the equivalence point, but I do know that it is 1.420 moles per liter. So this is my H2SO4, and this is my NaOH. So I should start with the known quantity, and that's the H2SO4. So now the question is, how do I get moles out of this? Well, I start with 25 milliliters, and I'm going to go from the mole or the volume of that acid to moles of the acid, then to moles of the base from the balanced equation, then to the volume of the base. So this is just a three-step factor label problem. And I'm going to use the molarity to convert between volumes of solutions and moles. And I'm also going to use the molarity to go from moles of solution back to volume. And the coefficients in the equation are going to give me that mole of one thing to mole of another conversion. So starting with 25 milliliters of H2SO4, I can use the molarity of the H2SO4, 4.50 moles per liter. And in this case, instead of converting this to liters, I just said that's 4.50 moles per 1,000 milliliters. If I stop right there, I've got moles of H2SO4. And now I can convert from moles of that to moles of my unknown, which is sodium hydroxide, NaOH. There's 2 moles of NaOH for every 1 mole of H2SO4, according to the balanced equation. And now I want to convert the moles of NaOH back to volume of solution. And again, the conversion for that is the molarity. The molarity for NaOH is 1.420 moles per liter. And I want milliliters. So also, moles of NaOH has to be on the bottom of this next fraction. So how am I going to write that molarity in here? Is it going to be 1.420 over 1, or over 1,000? Or is it going to be 1,000 over 1.20? 1.420. Well, it's 1.420 moles. So that goes on the bottom of this fraction. So this is the inverse of the fraction that we would write for the molarity. It's for every 1,000 milliliters of solution, there's 1.420 moles. But this is still this molarity. Now, if I cancel all the units, milliliters of solution cancels there, moles of H2SO4 cancels there, moles of NaOH cancels there, and I get 158 milliliters of NaOH. So 2 kinds of titration problems. One where you're going to actually calculate a molarity of an unknown solution, and in that case you should use stoichiometry to calculate moles of that unknown and then divide by the volume of the solution in liters. The other type of calculation is what volume of a titrant would you need to titrate a known quantity of a known concentration, and in this case it's just a 3-step factor label problem. We will be doing a lab, actually we'll be doing a couple of labs involving the process of titration in the next couple of weeks. In this diagram, I just wanted to point out something about a burette, which is this tall piece of glassware that we use to measure our titrant. And if you've never used a burette before, one of the things that's kind of confusing is if you look at the scale on a burette, it's actually upside down. So when you fill a burette, there's a valve at the bottom that you close, and then you pour your solution in very carefully until it's at or close to the 0 mark. Now, it seems kind of odd that this is 0 when this thing is full, but this isn't used to measure how much is in it. It's not like a graduated cylinder where you figure out the volume of a liquid by reading this meniscus. A burette's used to measure how much of it is delivered, or actually how much comes out of this. So when it's filled, we're at 0. And if you open the valve and you end up with a volume down here somewhere, and let's say that that was right on 2.50 milliliters, And my beginning one looks like it's at a little bit past 0.2, so this would be 0.25 milliliters. The difference between those two tells us how much has actually been delivered. And that's what we're interested in. What volume actually came out of this? All right. So that's it for titration. Another type of quantitative analysis that we can do is something called gravimetric analysis. And this is, again, just a stoichiometry problem involving a specific kind of measurement. And in this case, usually we have some sort of sample that we are trying to find the amount of, and we use some sort of chemical reaction to remove it from the system. For example, most commonly, the analyte can be subjected to precipitation. Okay, that's one way. Another way that we can measure the amount of something in a solution is if we just precipitate it out and dry it and weigh it. Okay, so here's an example of a gravimetric analysis problem. If I start out with an unknown mixture that has a mass of 0.450 grams, and in that mixture there's magnesium sulfate, but there's also other stuff, and it's dissolved in water, and I want to know how much of this 0.450 grams is actually magnesium sulfate. That's the question. What's the concentration or the mass percent of magnesium sulfate in that mixture? And it says that we dissolve it in water and we treat it with an excess of barium nitrate, which gives us a precipitation reaction where we get 0.6168 grams of barium sulfate, because barium sulfate is insoluble. So if I combine these two solutions, I end up with this as a precipitate. And I measured the mass of the barium sulfate. And I know that it weighs 0.6168 grams. The question is, how much magnesium sulfate did I have in order to make that much barium sulfate? So this is just a stoichiometry problem. So I'm going to go from grams of barium sulfate to moles of barium sulfate. And then I'm going to go to moles of the thing that I'm interested in, which in this case is the magnesium sulfate. And then back to grams of magnesium sulfate. And if I know how many grams of magnesium sulfate there were in my sample, and I know that the original mixture weighed 0.4550 grams, I can calculate the percent of that mixture that was magnesium sulfate. So this is our stoichiometry setup. And if we start with 0.6168 grams of barium sulfate, to convert that to moles, we use the molar mass of barium sulfate, which we get from the periodic table. And I know from the balanced equation that there's 1 mole of magnesium sulfate for every 1 mole of barium sulfate. And then again, from the periodic table, I can calculate the molar mass of magnesium sulfate and say that there are that many grams in 1 mole. So if I do that problem, I end up with 0.3181 grams of magnesium sulfate. And recall that we were interested in what our percent of our original compound or our original sample was magnesium sulfate. So our original sample had 0.4550 grams of a mixture. And this calculation tells us that of that 0.4550 grams, 0.3181 grams of it is magnesium sulfate. So what percent is that? Well, percent is just the mass of the part that we're interested in divided by the total mass times 100. So to calculate that percentage, we would just take the mass of the sample divided by the mass of the magnesium sulfate divided by the mass of the whole sample times 100. And we can say that that's original mixture contains 69.91% magnesium sulfate. So those are a couple of examples of quantitative analysis setups. And quantitative analysis setups are essentially just stoichiometry problems involving specific types of experiments. That's it for Chapter 4. Our next lecture will be the beginning of Chapter 5.